All right, good afternoon. Recording is on. Our colloquium speaker today is Dr. Justin Perron. Dr. Perron completed his PhD in physics at SUNY University at Buffalo in 2012, and then spent 3 years working at the National Institute of Standards and Technology. Since 2015, he has been an associate professor of physics at California State University, San Marcos. His research is in experimental solid-state physics with a primary focus on silicon quantum electronics. In today's talk, he will discuss how advances in quantum information science enable researchers to experimentally investigate the aspects of quantum mechanics, including a discussion on gate-defined quantum dots, how they can be used to examine the quantum measurement process, and help shed light on what constitutes a measurement and the collapse of a wave function. Please give a warm welcome to Dr. Justin Perron.
Thank you very much. Yeah, what she said. That's me. I want to thank everyone for having me today. This has been a great day, seeing all the interesting labs, meeting some of you students out there. Some of you, especially looking at some of the previous colloquiums, have probably heard some of my intro and a lot of things I'm going to say. But I'm going to talk about essentially just the things that interest me and what sort of drives a lot of my research, and which is broadly in quantum information science, but really a sort of unique feature of it that I really like, and using it as less as a practical application and more as a way of just sort of answering fundamental questions that I sort of tickle the brain sort of thing. So naturally I am on Zoom. So quick outline of what I'm going to do is I'm going to give some sort of historical context of why I think it's an exciting time we're in right now with quantum information science and what a lot of people call the second quantum revolution. And then I'm going to go into an introduction to sort of silicon quantum technologies as a whole, which is broadly the field that I research. You know, what are qubits and the quantum mechanics, sort of basic intro to a qubit, how gate-defined quantum dots in silicon work and the concepts of them, and then how we can use those as qubits and how to read out and measure them. And then hopefully we all sort of get that understanding and we can start to talk about, all right, now how can we use this for a measurement that I'm recently proposing that I think is really interesting. So yeah, let's go through some history. First quantum revolution about 100 years ago, you know, start of the 19th century. There were all these measurements. If you've taken quantum mechanics and that, you've probably heard of a lot of them, the ultraviolet catastrophe and black body radiation and photoelectric effect, things like this that were experimental results that were really difficult to sort of reconcile with classical physics. We couldn't do it. So it led to some, you know, theoretical advancements, the Bohr model of the atom, wave mechanics, and the Schrodinger equation, uncertainty principle, all these things that sort of resulted in what we now call quantum mechanics. About 100 years ago, changed the way we understand the universe, right? And you've probably all heard popular science and different sort of things about how counterintuitive and weird quantum mechanics is. Things involve like superposition, particles in two places at once, and entanglements, measurement and, you know, wave function collapse and all these things. You know, Schrodinger's cat, famous thought experiment, kind of used to highlight how ridiculous quantum mechanics is. And, you know, you can't get near Halloween without quoting Einstein's spooky action at a distance for entanglement. But all these really sort of counterintuitive properties that change the way we understand the universe. But immediately after all of this theoretical advancement, there started to be technological applications that were developed and enabled by this new understanding. You know, lasers, atomic clocks, transistors. It's hard to overstate how much these technologies have sort of revolutionized and changed the world. There's probably billions of transistors in this room, in our pockets, on our phones, the computers, that just, you know, everything we do now involves these technologies, all of which are enabled by our understanding of quantum mechanics. But, and this is sort of what I would call the first quantum revolution. But one of the things I like to highlight about this and these technologies is, although they're enabled by our understanding of quantum mechanics, none of them actually involve the weird parts of quantum mechanics, right? Like nothing really fundamental in the operation of a transistor involves entanglement and superposition. You know, to first order, we're not really worried about that when we explain how they work. But fast forward 100 years to now, And we're in what a lot of people are calling the second quantum revolution, where given 100 years of advancement and understanding, we're at a point now where we can actually engineer individual quantum systems and control them well enough that we can take those counterintuitive properties like superposition, entanglement, and measurement, and use them as features and sort of make technologies that take advantage of those aspects. And there's sort of the three pillars of quantum information science that come with that. Quantum computing, which is just a new paradigm of computing that can potentially solve a lot of problems much faster than we believe are possible classically. The big impetus with this was Shor's algorithm that in 1994, he developed an algorithm bearing his name that can apparently factor large numbers into their primes, which has implications for national security and a bunch of reasons. But yeah, so a lot of money went into the field to sort of show, can we build these things and use them? Quantum sensing uses the sensitive nature of these quantum states and that to develop detectors beyond the capabilities of classical detectors. Quantum communication basically takes the idea of quantum measurement and the fact that measuring a system affects that system and uses that to set up provably secure communication channels. But all of these applications, and here's just a slide. I'm not an expert or in any of these things, but these are all active fields of research that people are trying to apply these technologies to. Everything from submarine detection using magnetometry, flight path optimization, simulating complex quantum materials more efficiently. All of these things are being pursued as possible potential uses for these technologies. And with all of these uses, that's funding and interest, right? We're in the 5th year now, I believe, just finishing the 5th year since the passing of the National Quantum Initiative, which was a federal bill allocating $1.2 billion of funding to help America stay as the leader in the research field and make sure that we benefit from all the technological advancements. There's been private sector investment, a lot of startups trying to build quantum computing full stack. IonQ was the first publicly traded quantum computing company a year or two ago. Rigetti's another one that's come in. A lot of major well-known companies like IBM has a huge investment in quantum. This is, I think, an older version of their roadmap of how they plan to build out a large full quantum computer. Google has another one, Amazon, a lot of investment from the private sector. Google, a couple of years ago claimed what they refer to as quantum supremacy, basically on one of their quantum computers, performed a task that they argued was not possible to do on a classical computer. Wasn't a useful task, but I think what it did highlight that you can use these things to do stuff we previously couldn't. So still a big milestone. But anyway, lots of technology, lots of interest. There's also products coming to market, from dishwasher detergent to coffee and toothpaste and hair products and deodorants and energy bars and booze, one of my favorite. And it's in sci-fi films everywhere. And there is a lot of hype with all of this influx of money that kind of, like, I caution anyone to go on LinkedIn and look at thought leaders in quantum selling you their snake oil. But there is actually real research and a lot of potential in this field to really change the world and do things. As an aside, one of the potential applications is simulating nitrogenase to help with Haber-Bosch. But anyway, hopefully what I can do today is sort of introduce the base unit of quantum technologies, the qubit, and describe how we can actually make those in the silicon system, and hopefully get us all to understand that. So quantum technologies, the basic unit is the qubit. So how many people know what a classical bit is? What is it? Someone? Yeah, it's a 1 or a 0. Any sort of mutually exclusive states can be a Q. So coin, heads 1, tails 0. Anything light on, off, transistor on, off, 0s and 1s. You can encode information in 0s and 1s and do it that way. A quantum bit is the same thing. You have some distinguishable states, whether it's the ground state of an electron and an excited state, or the spin up state of an electron, spin down state. Any two states that you can label, call one 1, call one 0, that behaves quantum mechanically, follows the rules of quantum mechanics, and you have coherent control of that behavior. right? So like I said, this could be the ground state of an electron in the first excited state. This could be the spin state of a nucleus and a different spin state of that nucleus, anything like that. So what do I mean by obeys the laws of quantum mechanics or coherently? So although there are only, if I were to measure this state, I get one of these two outcomes. The true state of that system is described by what we would call a vector in a complex Hilbert space, but basically a linear combination of those two basis states, right? So if you're not familiar with the linear algebra and vector spaces, maybe this is a bit foreign, but I can guarantee you, if you've taken an intro physics class, you're familiar with these types of vector spaces. If you consider position of a particle that you've studied in intro kinematics, it is a vector in a vector space. And if you consider a two-dimensional vector that's got an x basis vector and a y basis vector, and the state of that particle is described by some vector r that can be a linear combination of those two basis states. Quantum mechanics, same idea. You have a Hilbert space that's spanned by two basis states, and your true state of that quantum mechanical system is a vector in that Hilbert space. It's different because the amplitudes of this linear combination are complex, but conceptually it's the same thing. So if I can take a two-level system like this and I can control these alpha and betas and what it is, I have a good qubit, right? I have to be able to measure it, obviously, but that's the gist of what we're trying to do. And a cool thing about the quantum mechanics of this is if I make a measurement of this quantum state, I don't get that quantum state as the result. I get the 0 or the 1, right? And that's a probabilistic measurement, and the probabilities of those measurements are related to the amplitudes in that linear combination. So again, many of you probably are familiar with this, so forgive the redundancy, but that's one sort of interesting thing about the quantum mechanics of this. The other thing is, after the measurement, the system is now no longer in that state. I've affected it and sort of collapsed it into one of these basis states. So I measure this state psi, I get either 0 or 1 probabilistically. After I've gotten that result, the state is no longer psi, it's 0 or 1 or whatever the outcome was. So that's kind of cool. And where the field is generally now, field's a lot of places, but I think we're still at the how do we make good qubits? So the challenge with quantum information science and technology is what's going to be the best two-level quantum system that I can control the best and measure the best and do that. There's superconducting qubits where those states are currents in those superconducting circuits. There's trapped ions where they're electron states on trapped atoms. The area that I like and am most interested in is silicon quantum electronics, which basically are electronic devices in the semiconductor silicon that has the ability to isolate individual electrons in that device, right? And then use the quantum states of those electrons in that semiconductor as your bit. And there's tons of ways to do this. So what I'm going to start now is trying to explain how do we do that? And I didn't say this at the start. Anyone who wants to stop me and ask questions or whatever, please don't hesitate. So how do we trap single electrons in silicon devices? And the way I like to sort of think about this or introduce this is sort of with a question of, we're all familiar with charges quantized. Electrons got the fundamental charge on an electron. We learned in our modern physics classes all of these things. We also learned in our circuits course that if I hook a battery up to a light bulb, current flows and all. Why is it that when I'm looking at the applications, essentially circuits, why do I not see any real evidence of that charge quantization, right? And if I can answer that, maybe I can start to say, okay, well, I can make that happen. Does anybody have an answer for this? Why, if I hook up a battery to an incandescent bulb, do I not see any effects from like single electrons? Yeah, so that's the first answer that I would come up with too, is there's just too many of them, right? Like 1 amp is 10 to the 18 electrons per second going through that wire. You're not going to notice 10 to the 18 plus 1, right? So like it's just all washed out. Okay, that's true. It's kind of an engineering problem though. Like scientists can now measure time to that accuracy. So it's not hard to imagine maybe we develop an ammeter that can tell that thing. So it's not really a fundamental reason. Another reason that I think is the way I like to think about it is I don't think of charge flow in conductors as quantiles. Like I don't think of an electron bouncing through a wire just the same way I wouldn't think of water flowing through a hose as H2O molecules bouncing around that hose. I just think of that liquid, right? If you've taken solid state physics, covered band theory, those conduction-based states are delocalized states across that whole conductor. So you don't think of electrons flowing through a metal, you think of this sort of displacement charge like a liquid sloshing back and forth. And one example where you can see that is you can charge a capacitor with an arbitrarily small amount, like I can put less than an electron of charge on a capacitor, right? So it's clearly just you're sloshing this liquid through your conductor. So the question is, if I want to isolate individual charges, I have to somehow break up these non-localized conducting states. And the way we can do that is with what are called tunnel barriers or tunnel junctions, right? So many of you may have heard of tunnel junctions. The gist is you take a region of space where electrons aren't allowed, right? So the easiest way I can think of doing this is if I take an aluminum wire, aluminum's a conductor, electrons are allowed everywhere, oxidize it. Now there's a thin insulator where free electrons aren't allowed, and then put another aluminum on the other side. I'll have conductor, fluid of charge on both sides of a region where they're not allowed. And if I were to apply a voltage or hook up a battery to that, raise the energy of the electrons at the one voltage, and although they don't have enough energy to overcome that barrier, so classically they would have to stay on one side, quantum mechanics and tunneling says there's a finite probability that they will tunnel through, so I will still get conduction through that tunnel barrier. But the key point is the electrons are on one side or the other of that tunnel barrier. I've split that sort of sea of electrons into two seas now. So I haven't really isolated anything, but we can start to see how we can use this to actually isolate electrons. If I put a second tunnel barrier on the other side, I can set up the same thing where I hook up a battery, raise the energy of those electrons. The electron's going to tunnel off to that side, but now it's stuck between these two. So now when this electron wants to come over, well, it's got to go, if this is small, close to that electron, the Coulomb repulse. So the energy is a bit higher and it's going to go to there. And if I keep doing this, eventually it's going to be uphill and it's not going to want to go there. So it's going to be blocked and we're going to stop that tunneling process and isolate electrons here. This is kind of hand wavy and not really work. If this is the case, that electron is going to go off and then the next one's going to go. So we're still not quite there yet. But if I make this small enough and that, we can start to actually model the energies involved with this, right? So we can set up, if I have just two tunnel barriers along a conducting path, I can set up a simple circuit model that works quite well at explaining this behavior where I have, my ground, battery hooked up to the one conductor, a tunnel barrier, my little island or quantum dot if you want, another tunnel barrier on the other end of the circuit. We can model these tunnel barriers as essentially capacitors. Charges are on one side or the other with a really high resistor in parallel. You can essentially ignore the resistor for this calculation. And I can think of, all right, if I apply this voltage and I have N electrons in the middle there, I can calculate the energy in those fields. Of the capacitors, 1/2 C delta V squared for both those capacitors and figure out the energy of the system with N electrons on the dot. And I can do the same thing for N-1 electrons on the dot. And if I take the difference, that sort of gives me the energy required to add that N electron to that dot, which we'll call the chemical potential. And when you go through that calculation, you end up with this ladder of states, of chemical potential states for different numbers of electrons on your quantum dot, right? And if you know how chemical potentials work, if I apply voltage on the one side, I've raised the Fermi level or chemical potential here. Things like to flow downhill in chemical potential. So if I have a downhill path through this device, I'm going to get current through the device and the electrons are going to tunnel sequentially through, and I'll see a current and I'll be able to measure it, but it'll be formed from individual sequential tunneling events just happening really fast. Right? If I make that dot really small, the spacing between those levels get bigger because those electrons are closer together. The energy required is more because I'm putting them closer together. And I can get to a system like this, set up like this, where Coulomb blockade happens, where the electron tunnels, goes into occupies this chemical potential state. The next state is an uphill thing, so it's not going to flow. There's no electrons going to flow to it. This one can't leave because it's uphill to there. So we're in what's called Coulomb blockade, where essentially the presence of this electron on my quantum dot blocked any other tunneling from happening, right? So that's the gist of how these devices work. We want a bit of more control over this than just the one voltage. So what we can do is put a metal gate just nearby that dot that's capacitively coupled to it, where I can control the voltage of it. So if I control the voltage here, I apply a positive voltage, that's going to have a field that sort of raises the potential here. Electrons like higher potentials, so it'll lower the energy of those states. But essentially, by going up and down in voltage, I can raise and lower those chemical potential states and go into and out of Coulomb blockade. So a standard measurement of this type of device looks something like this. I've got my voltage hooked up through my tunnel barriers, so I'm measuring current along this loop, and I've got a voltage here. And if it happened to be set up where the chemical potential slide like this, I'm not getting any current. I'm in Coulomb blockade, and then I increase this voltage, it lowers those states, and eventually I bring one of those states into this conducting path, and I'll see a spike in current. Right? I increase the voltage a bit more, it comes down, I go back into Coulomb blockade, but I've added one more electron to that dot. If I increase the potential more, I bring it back out of Coulomb blockade, I see another spike, and then I keep going after that. And essentially, I see these spikes in current that are separating regions of stable charge state on the dot. So you can see spikes in current separating, there's n electrons on the dot here. I go past my next spike, now there's n+1, past the next one, now there's n+2. And it's easy to imagine, well, if I make it lower, I can empty that dot and go down to the final electron on it. So you can literally count how many electrons you've isolated in your quantum dot by making these transport measurements. And that's how we do it. This, I haven't mentioned silicon or any actual physical implementation yet, though. So
little stubble squares on the other side of your dot, those represent all sides of the gate, or just one of those color?
So this just this is my symbol for a tunnel barrier.
That's just one tunnel.
Yeah, this is one tunnel barrier. I stole it from review articles that always use. I actually have no idea. Well, that's a good question of why they use that symbol. But
two sets of tunnels, or just one set?
Yeah, no. So this is just one tunnel barrier. There, that's the second tunnel barrier.
Cool.
Yeah. So that's how single electron devices work in general. And you can do it in you can do it with that aluminum oxide thing if you want. Nothing about this is actually quantum yet, other than the idea of tunneling. We use silicon, and it uses just MOSFET physics. So if you know how a transistor works, might be redundant for you, but the gist is solid state physics in 2 minutes. How long do I have? I think we have time. I have a silicon substrate here. Silicon's a semiconductor at low temperature, no free electrons. So, I've doped the source and the drain with a bunch of phosphorus. It's added a bunch of free electrons. So these white regions conduct, but if I hook up wires, try to measure current through there, I'm not going to get any current. And that's because the conduction band states where the electrons have to be are much higher in energy, so none of them are occupied. But if I put a metal gate, separate it with some oxide or insulator on top, and apply a positive voltage, that lowers the potential energy of those electron states. It does what's called the band bending. And I can, by increasing that voltage, lower that conduction state until electrons occupy them and then turn on conduction. Right? It's physically what's happening. I put a positive voltage here. Electrons like positive voltages. I'm pulling electrons towards it until I get enough at that interface to conduct with. So the key conceptual idea behind these field effect transistors is that the voltage on the gate on top of the semiconductor determines whether the silicon underneath it is conducting or not, whether there's electrons there or not. And using that sort of concept alone, you can make devices, multi-layer structures with nanofab that can push and pull your electrons in the silicon to wherever you want and isolate them. So an example of one that I did with my time at NIST that's really, I think, a good idea, a good example of how this can be done is I take a silicon on insulator wafer that has top layer of silicon, and I cut out this nanowire, so 50 nanometers wide, really small wire of silicon, that's going to be where all the action happens. After that, I oxidize it, so it's insulated, not electrically coupled to anything else. And I put down some conducting lower gates. They're not metal, but think of them as metal for all intents and purposes. These are metal that I can control the voltages on by plugging it into, that sort of just come across that wire. Then I oxidize those and put an upper gate on top of the rest of the wire and cover it like that. So if I were to take a line cut down that nanowire there, schematically, it would look something like this, where I have the silicon nanowire underneath, the oxide separating it, those three lower gates, one near the source, one near the drain, one near the center, and then that upper gate on the top of all of them. So what I can do then is I apply a positive gate voltage to that upper gate to lower the conduction band energies and basically turn on conduction everywhere. I pulled electrons everywhere in my device. So this wire is now just conducting. And then with the lower gates, I can apply a negative voltage that's going to push the electrons away from underneath them, raise the conduction band locally, and make those tunnel barriers. Now electrons aren't allowed there. And I've isolated regions of charge between these lower gates by basically just using the electric fields of those gates to push and pull the electrons to wherever we want. And you can see signals in transport that tell you they're where you want them and things like that. So this is a really simple device in terms of how it works this way, but the field has grown and does much better things. Now it's from the same device run. We had two parallel wires connected by this coupling bar with a bunch of different lower gates, so you could isolate, quantum dot here, here, see how they talk to each other and that. I won't get into how it didn't work as we designed because it's still a pretty picture. But like here are some pictures from an Australian group at UNSW who's done some really good work where, this one, it has two lead gates that conduct underneath them, barrier gates that form those tunnel barriers, and plunger gates that do this. This one, much more complicated, essentially can put an array of single electrons in here and do a lot of things with it. But again, we're just putting electrons where we want that thing. And so to speed things up, none of that is a qubit, this electrons thing. So we can take, now that we have those qubits where we want them, what quantum state are we going to use our qubit? My personal favorite, because it's simple, is apply a magnetic field, and that splits the spin states of those electrons. The aligned and anti-aligned states, those are going to be our qubits. We have spin up and spin down, right? So the requirements of a good qubit, two states, be able to measure them. So how do we do that? Well, when you have a hammer, everything looks like a nail. Let's use another quantum dot. So we can isolate an electron here, and then we can have another electron here on this quantum dot that we're going to measure the same way we saw before. And if you think about how this measurement works, this voltage determines the voltage here and whether it conducts or not. This dot's capacitively coupled in the same way. So whether there's a charge here or not will affect how this curve looks. So if there's an electron there, I get the black curve. If there isn't, I get the red curve. It's shifted a bit. So this dot is a very sensitive charge sensor of this. So if I want to measure these states, what I can do, because measuring magnetic moments is too hard and they're too small to get that, is I can pulse my system to a state where if it's spin up, it has enough energy to tunnel. If it's spin down, it doesn't, and then look to see if I see that tunneling. So I set my voltages, so these are the states there, and one can tunnel, one can't. I'll be reading my quantum dot that's sensing it here, and I'll be getting that current because the electron's on the dot. If it tunnels, that curve all of a sudden switches to the red one, and I see a jump in current. So monitoring the current through one dot, if I see this jump, I know the electron that's my qubit left, which tells me it was spin up. So I do this spin to charge conversion, they call it. Blip tells me it's spin up, no blip, spin down. Right, so that's how we can do it. We also need to be able to control the thing. To do that, we just do NMR. So how many people know magnetic resonance sort of thing? Basically, if you have a DC magnetic field, and then you apply an AC field perpendicular to that on resonant, you can rotate that spin. So what we need to do is apply a perpendicular magnetic field to that dot. The way we do that is we have a wire next to it, and Biot-Savart has that right-hand rule. Currents go around. If I put an AC current through here, I get an AC magnetic field into and out of that page that does that. So what I can do is load a spin down, apply that ESR current for a given amount of time, pulse to that readout, see if it was spin up or spin down. Do that 1,000 or so times. and get the statistics of how many were up or down. And you can see these really nice Rabi oscillations of the spin rotating depending on how long I apply that pulse for. So we have coherent control, we have readout, we can make those measurements. This is a good qubit. Lots of applications in those technologies, trying to build quantum computers and such. Cool. Tell the funders that, they'll give you money. I don't care about that. They allow you to ask questions like, what constitutes measurement? Right? Like, we can control these systems. Let's think back to what a quantum measurement is. We have this coherent state. It's a mixture of those. I make a measurement, I get up or down. Afterwards, it's collapsed into up or down, right? So let's think about this actual measurement we made. We're measuring current and whether the device tunneled or not. So if it was spin up and it tunnels, I see that blip in current. Pretty obvious answer. Here, where it didn't tunnel, I didn't see a tunnel of it. That's all I know. Did that collapse the spin state or not? Is a question you can ask. Did this not tunnel because it collapsed into down? Did it not tunnel because it never actually collapsed the spin state? Did it collapse into up and just not have time to tunnel yet? All these things take time. So we have the ability to test this now and see and investigate that. So basically, the proposed experiment I have to do this is load a spin down spin electron, do our ESR rotation to put it in an equal superposition of up and down, and then pulse to that readout state and look at, for a certain amount of time, and then pulse back down if it didn't tunnel. And you can ask, does that constitute a measurement of the spin, those negative results? And the way you can sort of gain insight to that is after that, do another manipulation of that spin, and we can sort of see how what happened here will affect what happened from this manipulation. And sort of the naive approach that I first had when thinking about this is there's three possibilities. Either it didn't collapse, there was no measurement, it collapsed into down and that's why it didn't tunnel, or it collapsed into up and just didn't have time to tunnel, right? And you can think of what would happen with that subsequent manipulation should that happen. If it didn't collapse, that subsequent manipulation is just going to be a continuing Rabi oscillation that starts from that 50-50 superposition. If it collapsed to down, that oscillation is going to start from down. If it collapsed to up, it's going to start from up. So we've sort of mapped whether the state collapsed or not to a phase shift in our Rabi oscillations from our standard measurement. And, if you do the things we always do, assume things are random Poissonian processes or whatever, and the probability that there was no tunneling event decays exponentially with the tunnel time, probability of collapsing decays with some collapsed tunnel time. You can see how those three contributions would come in. So no collapse is this one. It starts from the middle, but the contribution from those quickly decays because the longer you glanced at it, the more likely it was to collapse. The spin down is this one. It starts with hardly any contribution, but that quickly grows because more and more will have collapsed. The collapse to up's a weird one you'd think of. It's if I only glanced at it for a nanosecond, not much has collapsed, so there's not going to be a contribution. So it's going to start to increase as we look longer. But then the longer I look at it, the more likely the collapsed up will have tunneled off. So it's going to decay at the end. So you're kind of competing best. Add them all together, and you're going to get some weird approach. And you see, when we simulated this, you see a phase shift that comes in at essentially whatever you assume that collapse time is. Insightful, nice way to think about it. I called it naive because it's not really, there's better ways to think about it, and how the measurement approach works. And we use what we call density matrices. So those typically, in my experience, aren't taught in most intro quantum courses or things, but the idea of how density matrices works, rather than describing your state as a single vector in a Hilbert space, you do the outer product of it with itself, and you get this sort of operator that has the same information in it. Time evolution of that state's described the same unitary evolution way you would with the standard quantum mechanics approach, except for you have to do it on both sides of the operator because you're doing it to both things. So we're doing a lot of the same stuff. Where's the advantage? The advantage is it's really useful for describing mixed states rather than pure ones. So if you look at that situation where did it collapse? I don't know, not like you can basically make one density matrix that includes all of those just by adding them together, weighted by their probabilities. And when you do that, you can use this in a quantum measurement formalism to sort of describe how quantum measurements should work. So what do we think? This is a question I always like, and I have my prop. I told you I was going to use it. What is a measurement and how does it work? So if I have my water bottle here, it's got color, it's got mass, it's got all those things. If I ask you to tell me the mass of this water bottle and measure it, what would you do? Yeah, you take it and put it on a scale or something, right? So if you step back and kind of think about what we do when we measure things, we take a system of interest that we don't know everything about, and we take the scale or the spring scale, whatever you use, something you know a lot about, your probe, and you turn on an interaction between them and look at how the probe changed. And you can infer, since you know everything about your probe, you can infer things about the system that causes those interactions. Quantum mechanics should work the same way, right? So I have my target system, my spin, that has its Hilbert space and its density operator that describes its states. I have my probe and my environment that has its Hilbert space and its density operator driving its state. When I make my measurement, I turn on an interaction between them. And quantum mechanics should work, be able to describe that full system with its larger Hilbert space and its larger density matrix, and just see how that evolves given that interaction, right? So I take the two subspaces density matrix and I form the tensor product operator, both of those, the larger density matrix for the full system. I see how that evolves given this Hamiltonian. And then when I'm done my measurement and I turn off that interaction, I basically just throw away all the probe stuff to get the state of the target. You do what's called a partial trace mathematically, or discard the environment, and you get the density matrix for your quantum system after that measurement. And it actually defines what are called these measurement or Krauss operators for the possible outcomes of that measurement. And it's basically the state they're in. But you can determine what the state of that system is after that measurement turned it on. So what we and some friends did and colleagues did is looked at that proposal I talked about and used this sort of measurement formalism to analyze it. And we used 3 different models for it. The one, which is what I would call a standard approach, where the only interaction is a tunneling interaction for that readout. And you essentially get measurement operators that look like this, square root of the probability that it didn't tunnel. We looked at a 2-step model that it's kind of a heuristic where the tunneling and this collapse of the spin state are sequential things. You can't have tunneling until it's collapsed. We got 3 measurement operators that sort of outline the possible results. This is similar to that naive approach where either it didn't collapse, it collapsed to up but didn't tunnel, or collapsed down and didn't tunnel. Then we looked at what we're going to rename, but currently a hybrid thing where you can have interactions that cause it to tunnel. It's allowed to tunnel from a superposition state, or it can collapse due to some other interaction and then tunnel. And we got similar operators. The probabilities are calculated differently. But the cool thing is we looked at these 3 models in that experiment, and you can have, so these are all simulated with the same time scales and all our assumptions, and you get different outcomes for those different models. So we can actually tell, is tunneling that 1-step product, is interactions with the environment causing collapse, or various things like that to highlight, because these look kind of similar. This is a color scale, is the probability. I should probably explain this. Color scale is the probability of getting a spin up. So these are the Rabi oscillations. So you see that phase shift kind of come in the longer you look at it. If you take a line cut through there, you see 3 distinct things from those 3 models. So all that to say is someone make the measurement and tell us which is real. But I think what I kind of want to end on is, you can analyze these things. What I think is really cool is we are at a state now where we can control that. That's a feasible measurement. There are groups who, if they invested some time, could make that measurement and give some insight into what's happening in that measurement process. And you can start to ask what the question no quantum mechanics professor ever wants you to ask is, what's measurement? We all start. I had an exam today at my school. Quantum mechanics has postulates, the states described by a vector in a Hilbert space. There's operators associated with measurements. The only outcomes are the eigenvalues, and it collapses the state after the measurement, and time evolution is a Schrodinger equation. No student ever has raised their hand and be like, yeah, but what's the measurement? Right? That is a hard question, but we have toys that can actually get at that and answer it now. The way I think about it now is, can you just, the whole world's quantum, at some point, like we should be able to just describe our measurement tool and thing as a larger quantum system that evolves unitarily, but somehow there's always this collapse postulate. Can you describe that non-unitary collapse with a unitary process of a larger system? I think that the whole idea breaks down to irreversibility. So at some point, like if I have control over that system, I can undo the manipulation I did. At some point, there is some interaction I can't undo. And typically the way I think is it's some coupling to some thermodynamic system that just has too many degrees of freedom that it's never going to come back. And I can't do that. And we can now, if you think about it in the experiment I proposed, that thermodynamic system's obvious. I'm tunneling that electron onto a Fermi sea of electrons that has so many degrees of freedom. That's the thing that's causing the collapse. That's where I make my Heisenberg cut, as they say. So I have my dot here, it's going to tunnel off. I'm going to see whether it happened here or not. That's the thermodynamic reservoir. We expect that tunneling interaction to be the thing that describes the collapse of that wave function. You can do that. We can now set it up though, instead of tunneling to that thermodynamic reservoir, why don't we tunnel it to another dot? Right? This has actually been done. People in my field have made qubits where the electron's position on this dot or that dot is the degree of freedom that they make their qubit, and they use this tunneling interaction to coherently evolve that system. But they also use it in more complex systems to do this soul spin to charge conversion, where it's a discrete readout event of this. So how can we use that same tunnel interaction to do unitary evolution in some cases, when I want it to be my qubit, and somehow discrete wave function collapse when I want to do readout of just this qubit? I don't know. Is this the thermodynamic reservoir in that case? So, but like we can start to, you can imagine setting up these sorts of experiments and thinking at it and actually getting experimental data that feeds back on those sort of, I don't know if you're at all like me, those brain itches of like, I don't know how that works. But I can measure, and that can tell me and at least help guide how I think about it. So I'm very happy to be alive in this exciting time where all the things I don't know, I can actually now turn some knobs or propose turning knobs that groups can feasibly do and guide my thinking on it. So I think I don't know if I've gone over. Have I gone over? In summary, we're in the second quantum revolution, which is an awesome time. There's a lot of potential applications and things that will hopefully change the world for the better. But we're engineering quantum systems, and I think sort of the coolest part of that is we can now just play games with the universe and start to probe all of those fundamental questions that are never quite answered to some satisfaction. We can get experimental data that feedbacks directly on how to think about this. So with that, I want to thank you all for listening and having me out here. I want to thank Mike Stewart Jr. and Emily Townsend from NIST, who's worked with me a lot on this and other projects, and all my current lab members. Former lab member just graduated and is starting a PhD at UCSD, and my two current students who are undergrad students who are actually, we're trying to rewire our Dill fridge so we can actually try to do some of these things maybe in our system and do that. So really exciting semester because Maria has made a lot of progress on our setup and hopefully we cool down tomorrow. Anyway, I'm rambling. If there's any questions, thanks.
Thanks, Dr. Perron, for our wonderful talk. We'll open it for questions, starting with Stephen.
So, if I understood in your system, you were treating like spin up and spin down as your 0 and 1.
Yes, that's one of the
the phase essentially to see if you were basically if it was collapsing in one way or the other. Right,
so
to see if it was flipping.
The proposal involved, yeah, so the proposal was to use the lost DiVincenzo qubit as thing. So use this magnetic Zeeman split spin states as your 0 and 1, and then the proposal was rotate that, do an X rotation around an axis and go down, let it evolve, and then do another rotation to see if it comes back and see how looking at it in the intermittent phase affects liquids. the
So
subject.
in this system, is it, then I guess what I would want to ask, is it not possible for it to have that phase change on you once you put it into that basis?
So once we put it into like the X, is
Yeah.
it gonna process in
It
that?
has to
So-
stay in that basis.
So the state will evolve if it's not in one of the
Sure.
eigenstates. So the idea is in so we're in the rotating wave approximation, I guess, would be the one thing. So like in that state, if once we rotate down in that coordinate system, if we rotate to X and put it in Y in that DC field in the rotating wave, it's going to stay in that Y until we do the other one. In the physical space, it is going to be processing and all that. But it's as I started working on this and went more and more, there's a whole field of weak measurement theory that comes into this. And the gist is if you want more information on the state of a system, you have to do some tomography and manipulations of those things. So the gist is set it up, do your weak measurement, do subsequent manipulations so you can get the true state that you started in. But I guess that's a rambly way of saying yes. It is changing, but I don't think that is the killer.
So when you're talking about like what is and isn't measurement, is there like a gray area of like an indirect measurement, like when you're looking at like current spikes versus like I am looking at this electron and I know exactly what it's doing, and how do you like shrink that?
So I think that's a very interesting field. So I on one hand, so there's things like non-demo. So I guess maybe there's donor folks who will put in a phosphorus atom rather than doing an electrostatically defined well where you isolate the electron. I'll put in a phosphorus atom and that'll bind my electron and I can look at that electron. The phosphorus nuclei is also a qubit, right? So you can do all of these things we're talking about with the electron, and the resonance frequency that you do the manipulation depends on whether the nucleus is up or down. So you can use the electron to measure the nucleus, and it gets weird. You get non-demolition states where you can collapse this up or down, but since you didn't get rid of the nucleus when you did it, you can do subsequent ones. And I don't know if that's the gray area, but there's whole strength of measurement sort of thing where I don't know. Yes, I guess is the clear answer. There is gray areas all over.
So question of the validity based on the type of measurement that you're doing.
The validity,
Like
so
is one type of measurement always going to be more reliable than the other in the system?
so in that case, if you do, there's a thing called non-demolition measurements where you can make repeated measurements of the same quantum system. So these tunneling experiments, if it tunnels off, that electron's gone. So you can't remeasure it. In the nuclear spin qubit one, you can use that non-demolition where it's essentially if the nucleus is spin up and I have an electron on here, the resonant frequency, this has a magnetic field, so the resonant frequency is different than if it was down. So I can put this electron in, try to manipulate it with a given frequency, see if it worked. If it didn't, I was off resonance, this must be up or down. You can try to distinguish them. But the beauty part is I can do that with 100 different electrons for the same nuclei, and you can get better and better fidelity readout of that measurement because you're making repeated measurements of the same one, and that non-demolition repetition can give you stronger confidence in your result. I don't know if that's what you're talking about versus these destructive measurements where it's one and done, and was your signal to noise good enough to actually pull off? I don't know if that answers. I said things.
What temperatures, like what temperatures are you typically operating at, and then what's like the time frame for the
So the fridges typically have a base temp of sub 50 millikelvin. The odd thing that's cool though is the electron temps probably at 100 or 200. So you can actually map out the Fermi distribution of those reservoirs, and the temperature associated with those is a couple hundred millikelvin. That Australian group has done some work that shows that it still works up at a Kelvin without much degradation to stuff. Timescales, the ton of my understanding. So I said we a lot because I'm part of the field. So I haven't done the coherent readout stuff. The time scale is typically the tunnel time is the biggest thing. So the you pulse, and there's a trade-off between you wait there forever or not. But I think low microseconds is what they're looking for. You need, so I'll caveat it with, I'm not the one who's done these measurements, but talking to the folks who do, my understanding is, you need a tunnel time so that you're seeing those blips quick enough so that, like, if you have to wait, 30 microseconds for a tunnel event to happen, you don't know what's going to happen in those 30 microseconds. But if it's too long, it might dominate everything you did before that point. So when you're at that readout, you're in a very different state than when you're in a very stable charge configuration and doing your manipulations. So you need to have that tunnel rate tuned to quick enough that you can see that blip. And it's a balancing act. So if you look at these traces, somewhere in here, catch up. Sorry, should probably use this. It's like there's a huge lag. Okay, sorry. If you look at those pulses, oh my goodness, who made this talk? All I want to see, there it is. Come back. Really? No. I've outclicked myself. These. So you need to have the delay for the tunnel line to be quick enough that you see it, like you see it in a reasonable amount of time that you're doing it. But if it's too quick, the length of this blip is the tunnel time, right? Because this will tunnel off, but then a spin down is going to tunnel back afterwards. So this kind of gives you a measurement of the tunnel time. And if this is too short, your bandwidth of your measurement won't see that spike. So you start to miss tunnel events just because they were too quick. But if it's too long, then this whole thing takes too long and you've thrown away the baby with the bathwater sort of thing. So there's this balancing act. I need to be quick enough that I'm not waiting there for an hour, but if it's too quick, I miss everything. So they play that trade-off time. But this is, yeah, I think this is microseconds. So they're not 22 microseconds is roughly the tunnel time that from the one to the Red Bull.
Thank you so much for the talk. That was really, really powerful and a highlight of the semester. So the question I have, I was really intrigued by you talking about the collapse being a result of irreversibility. So normally when I think about irreversibility, I think about an environment with a set of degrees of freedom. Would there be any hope experimentally for you to design a probe or an environment with a countable number of degrees of freedom to see if you could stop collapse?
So if you're gonna speculate, let's speculate wildly. Yes, that's what I think. So, but I think this is why it's cool time is like literally it's just like the trapped ion folks putting arrays of these at, and what I think is interesting is if you're take the one subsystem you're looking at, and we can now control how coupled it is and to another system and the size of that quantum system. So you can start to say, okay, like they've done weak measurement stuff on where I'm tunneling to another dot, and depending on the strength of time, you end up just seeing coherent stuff back and forth where that tunneling comes back. But if I have that dot then further coupled to 4 more dots or something, like I don't think it's hard to imagine exactly what you're talking about, where how big do I have to make this quantum system to where this electron, sort of the information in its state leaves, but it's never going to slosh back like you'll see in the standard time evolution of not being in an eigen state of the larger. And I think, so that's exactly what I was getting at, is like where is that thermodynamic system and where do we draw, they call it in the field, I think, the Heisenberg cut. Like you have your quantum system and then way up here you have your classical meter. Where do we stop describing it as quantum? And I think we can do exactly what you're talking about, couple it to 4 others. Went to 5, and now that we're in the NISQ era where people are building 100 qubit systems, okay, yeah, run your algorithm, but like that's that question, and then play games there. but I don't have an answer, but yeah. It's-
Any more questions? All right, let's give a round of applause for Dr.